Electrical energy measurement 11. Calibration and testing of energy meters. The need for accuracy. Meter accuracy is crucial for fair billing and grid management. Over time, all meters, whether mechanical or electronic, can drift due to component aging, environmental factors, like temperature, or mechanical wear. Calibration and testing ensure the meter registers energy within specified tolerance limits. The testing environment. Testing is typically performed in a dedicated meter testing lab or on-site using portable equipment. The testing involves applying a known, controlled load and comparing the meter's registered consumption against a high-precision reference standard meter, often called a master meter. Accuracy class and tolerance. Meters are classified by their accuracy class, e.g., class 1.0 or class 0.2. This class defines the maximum permissible percentage error, or tolerance. A class 1.0 meter must have an error no greater than 1.0% across its operating range. Calculating percentage error. The fundamental test calculation is to determine the percentage error. Percent error is equal to actual reading, true reading, asterisk 100. A positive error means the meter is running fast, over-registering. A negative error means the meter is running slow, under-registering. No-load test, creeping. For induction type meters, the first test is the no-load test, or creeping test. With voltage applied but zero load current, the disk must not make a complete revolution. If it does, the anti-creep holes or the friction compensating device must be adjusted. Unity power factor, UPF, test. The meter is tested under a pure resistive load, power factor is equal to 1.0, at various current levels, e.g., 10%, 50%, 100% of rated current. This checks the primary proportionality between power and rotation pulse rate. Lagging leading power factor test. The meter is also tested at a low power factor, e.g., 0.5 lagging or 0.8 leading, to check the accuracy of the quadrature adjustment. This is critical for industrial meters to ensure reactive power is being correctly ignored by the active power calculation. Calibration adjustments. If the error exceeds the tolerance, adjustments are made. Friction compensation. Small loads are adjusted via a shading coil or short-circuited turns to correct for friction. Overload adjustment. Full load adjustments are made by slightly moving the braking magnet. Phase lag adjustment. Adjustments are made to ensure the shunt flux is exactly 90 degrees out of phase with the voltage, critical for accuracy at low PFs. Digital meter verification. Electronic meters are verified by comparing the rate of their impulse, LED, pulses to the reference meter. The pulse rate, often specified in impulses, kWh, must match the expected consumption based on the applied load and the meter's constant. Transition to energy management. We have covered measurement and verification. The final step is to put this data to use. Next, we will discuss how to interpret MDI and 2U data and use measurement for effective energy management and audit.